In this screencast, I'm going to present a proof of the theorem that every natural number greater than 1 has a prime factor. To start with, I will show you a quick outline of the strategy we're going to take. We are going to split a number into its factors until we arrive at one which is prime. This is demonstrated in this diagram. We start with our number n. We split it into two factors, n1 and n2. If neither of these are prime, then we split them further into factors. If none of these are prime, we split it further into factors, and we will continue this process until we arrive at a factor of n which is in fact prime. So to begin with, we state the theorem again. Every natural number greater than 1 is divisible by some prime number. We show this also in more mathematical notation. If n is an element of the natural numbers, and n is greater than 1, then there exists ni, which is an element of the natural numbers, such that ni is prime, and ni divides n. So, if the number that we begin with is already prime, then we are clearly done, because a prime number will have itself as a prime factor. However, if the number we began with was not prime, then we can split this number into factors. So, we find n1 and n2, which are elements of the natural numbers, such that n equals n1 times n2, and n1 and n2 are both less than n. If either of n1 and n2 were prime, then we have clearly found a prime factor of n, and so we are done. However, if not, then we must repeat the process of splitting up into factors. So, for n1, we say there exists n11 and n12, which are elements of the natural numbers, such that n1 equals n11 times n12, and n11 and n12 are both less than n1. We do a similar thing for n2. Then we look at the new factors we have found to see if any of them are prime. If they are, then clearly we are done. For example, if n11 is prime, n11 is a factor of n1, and n1 is a factor of n, so clearly n11 is a factor of n, and it's prime, so we have found a prime factor of n. If none of the factors we found were prime, then we have to repeat the process even further. We continue this, and we look at the factors we found to see if any of them are prime. If they are, then clearly, by the same reasoning, we are finished. However, if not, we must continue. Clearly, eventually this process will terminate. With each step, the factors are getting smaller and smaller, but they must always be positive whole numbers, that is, natural numbers, and so eventually the process will stop, and it only stops when we find one which is prime. Therefore, we must find a prime factor. To conclude the proof, I return to the diagram one more time to remind you of the strategy we took. We began with a number n. We decomposed it into two factors, n1 and n2. We examined these to see if they were prime. If they weren't, we decomposed each of these into two factors, and we looked at these now four factors of n to see if any of them were prime. If not, we decompose it further, and we continue this process until we do find a factor which is prime, and as such, we have proved the theorem that every natural number greater than 1 has a prime factor.